nearing the end of the year. We are looking today at arcs and central angles. Yeah, bud. And you wondered how we could make an entire chapter out of circles. Here we go. Green dot. All right, here we have a circle. Definition. We've got a number of new definitions today. A minor arc. An arc is nothing more than a piece of a circle, such as this red thing right here is an arc. If that arc is less than half of the circle, it's called a minor arc. Or in other words, if angle YOZ is less than 180 degrees, then arc YZ is a minor arc. Now, to name an arc, to name this red arc, we use its two endpoints, Y and Z. It's a lot like naming a segment. But we can't put a segment symbol on top because, well, it's not a segment. We certainly can't put a line symbol on top because it's obviously not a line. What do we put on top? We put on top the arc symbol. Now, don't get carried away with that. I see folks do, stuff like this and all kinds of weird things. Just make it a nice little gentle arc going from one end to the other. Make it look good. Mathematical maturity here. So the red arc here is known as arc YZ. An arc is cut off by an angle. This angle, by the way, angle YOZ is known as a central angle. That is a central angle. Why is it a central angle? Because central refers to the center. It's an angle whose vertex is at the center of the circle. By the way, recall that this circle has a name. It's called circle O, because a circle is named by its center. So this is circle O. And you'll also remember we have a symbol for the word circle because 6 letters is too much for us. We're practicing not only mathematical maturity, we're also practicing mathematical laziness. We have symbols for everything so that we don't have to write so much. So it's circle O. Our book writers love the point name O for the centers of circles. I guess because O looks like a circle. It troubles me. I'd rather use something else, but anyway. Circle O. So that means that, again, angle YOZ is known as a central angle because its vertex is at the center of the circle, point O. So an arc goes from one intersection point of the angle and the circle to the other intersection point of the angle and the circle. That's a minor arc. So a minor arc less than half the circle. A minor arc is cut off by a central angle that's less than 180 degrees. On the other hand, a major arc is more than half a circle. A major arc is more than 180 degrees. So the major arc would be this red arc here. That is a major arc, more than half the circle. Now, to name a major arc, how in the world do you name that thing? You can't call it YZ because YZ is understood to be the minor arc. So how do you name a major arc? Well, to name a major arc, we have to have 3 points. We need another point over here someplace, any old place, doesn't matter where, and we'll just call it, let's call it W. Now, to name the major arc, we would call it arc Y. Notice we'll start with one endpoint here, we'll end with the other endpoint here, and in the middle we put a point that tells us that we're on this side, not this side. So that's how you name a major arc. Minor arcs can be named with 2 points. And if it's not real clear from the diagram whether your arc is more or less or equal to half a circle, then it's okay to use 3 points regardless. Minor arcs can be named with 3 points, it's okay. But if it's obviously a minor arc, 2 points is fine. But if you want to name the major arc, you have to use 3 points to tell everybody that you're on this side, not this side. And this side pointer over here, I'll call it for the moment, is in the middle. The end points are at the ends. So major arc YWZ is clearly not the same as arc YZ. Arc YZ is the small arc, the minor arc. And can we name any other arcs here? We could name arc, how about arc ZW? Where's arc ZW? Well, arc ZW appears to be less than half the circle. Arc ZW would be this guy. Because it's less than half of the circle, we can name it with just 2 points. What if I wanted to name this? Let's change colors. How about, let's use a yellow. Let's make it a thick yellow. Suppose I want to name this arc from here all the way to there. That is what kind of arc? Yep, that's right, that's a major arc. So how do I name that one? The yellow arc would be called arc YZW. By the way, can I reverse that and call it WZY? Sure, you can reverse it. Wait a minute, no, I didn't mess up, it's fine. So these 2 points are the end points of the arc, Y and W. And the side of the circle that we're on, the side of Z goes in the middle. If I just said WY without the Z, where is arc WY? Well, arc WY is this red one. Arc WY would be the red one. Okay? So that's how we name arcs, and that's how we classify them as major arcs or minor arcs. Now you might be asking yourself the question right now, what if it is exactly half the circle? It's not minor and it's not major. Okay, true. If it's exactly half the circle, what do we call it? Half a circle is called a, and you've heard this word before many times, a semicircle. Semi meaning half. So a semicircle, this guy, for instance, would be a semicircle. Now how do we name that? Ah, yes, we have the same problem we had before. Naming it, if I say arc YZ, nobody knows whether I'm talking about this side or the green side. Which semicircle am I talking about? Therefore, we have to have a third point. So let's do it like this. If I put another point, say, over here someplace, and again, it doesn't matter where over there, let's call this W. What haven't I used? How about X? We'll put a point X down here somewhere. Point X. Now, the red semicircle would be called YWZ. The green semicircle would be YXZ. They both have the same endpoints, Y and Z, but the red one goes through W, while the green one goes through X. These are both semicircles. Oh, and by the way, don't forget some old terminology here. What's this yellow line called? Diameter. So a semicircle goes from one end of a diameter to the other end of a diameter. The green semicircle goes from one end of a diameter to the other end of that diameter. Oh, and by the way, just a quick review. The segment from here to here is called a radius. A circle has an infinite number of radii, and what's true of every single one of them? Every single one of these radii, they are all congruent. all radii of a circle are congruent. All right, now another definition. I already mentioned that angle YOZ is an example of a central angle. Angle YOZ is a central angle because its vertex is at the center of the circle. Its measure happens to be 50. By definition, strictly by definition, if the central angle's measure is 50, then the arc that's cut off by that central angle has a measure of 50 also. That's the definition of arc measure. The measure of an arc is equal to the measure of its central angle. That's all there is to that. Now that raises a complication. Because what if I have another circle? Let's see if I can do it this way. I'd like to have a nice neat circle here. Let's clone that guy. And let's shrink him down. Okay, what if I happen to have two circles with the same center? What's the measure of the green arc? Well, by definition, the arc's measure is equal to the measure of its central angle. That means that this arc, which doesn't have a name yet, let's say AB, the measure of arc AB is also going to be 50, just like the measure of arc YZ is 50. Now this is a little bit peculiar. If you have two segments whose measures are both 3, then by definition we know those segments are congruent. If you have two angles whose measures are both 37, then by definition those angles are congruent. We're used to the concept that if things' measures are equal, then they are congruent. Congruent meaning same size and shape. But here we have two arcs that have the same measure. But would you say they are congruent? In fact, I think I could be fancy here. Let's pull that green arc off to the side, and let's pull that red arc off to the side. They both have a measure of 50, but would you say that those two arcs are congruent? Are they the same size? No, they're not. The red one is clearly longer than the yellow one. Yellow, right, I'm colorblind here. The red one is clearly longer than the green one. They're not congruent. So it's kind of peculiar that if two arcs have equal measures, that does not mean they are going to be congruent. But that's how we talk about arc measure. The measure of an arc is equal to the measure of its central, its central angle. No matter how many circles I might have with that same center, this arc would also be 50 degrees. Even if I have a little one, hey, let's move this guy. Take that and move it down here. Even if I have a little circle here, this red arc has a measure of 50 degrees because it's equal to the measure of its central angle, which is 50. All right, so that brings up another question. That being the case, how do we deal with arcs being congruent? Do we have a definition of congruent arcs? Well, yeah, it's simply this. Two arcs truly are congruent if, number one, they have equal measures, but also if they are on the same circle. If, for instance, if I can clean this up so I can get rid of some of my junk on my bed. Let's get this cleaned all the way back up to, that's a good point. There. The red and the green arcs are clearly not congruent. They're not on the same circle. They are different size circles. They are different length arcs, but they do have the same measure indeed. But if I have another 50-degree arc over here, meaning that its central angle is also 50, then as long as they're on the same circle, then that arc and that arc would be congruent. If they have equal measures and they're on the same circle, then they're congruent. Or, yes, I know what somebody out there is thinking, if they have equal measure and they're on congruent circles, meaning circles that are the same size, then they're also congruent. I feel like there's something important. What about the measure of a major arc? There's a little bit of a problem with the measure of a major arc. When we start talking about a major arc measure, and let's get rid of one of these circles, let's get rid of that inside circle here. Okay. Suppose I want the measure of this major arc. Can we say that it's equal to the measure of its central angle? Well, not really, because in this geometry, unlike trigonometry when you get to pre-calculus, but in this geometry, we have agreed back in chapter 1 that angles are always less than or equal to 180 degrees. There's no such thing as an angle whose measure is more than 180. So how do we define the measure of a major arc? Oh, it's easy. To get a major arc, suppose this angle is once again 50. The major arc will be, what do you think a whole circle would be? 360. So a major arc is 360 minus the minor arc. So that major arc's measure, the measure of arc, no points here, let's call it x and y. The measure of arc x, w, y, x, w, y would be 360 minus 50. That makes sense, right? Otherwise known as 310. Okay? There's one other thing I forgot to mention. Maybe it's on one of the upcoming pictures here, boards, screens. I forgot to mention, although it should be pretty obvious, what would the measure of a semicircle be? Yeah, all semicircles have a measure of 180. Because a semicircle is cut off by an angle that happens to be a 180 degree angle. And for visitors who are watching this video, just a little disclaimer here. Some books claim in geometry that an angle measure must be less than 180. And if it is 180, we don't call it an angle. Well, in this book, we allow for 180 degree angles, and we call them straight angles. Yes, they're equivalent to lines. But this book does allow for 180 degree angles, but it does not allow for angles more than 180. It's all a matter of how you define your particular geometry. Everybody can make up their own definitions as long as they make sense, as long as they fit the overall scheme and don't violate any of the postulates or theorems. You can make up your own definitions. This book defines angle as being anything greater than 0, but less than or equal to 180. Okay, thought I'd throw that in there for visitors who are saying, that's just not right. Depends on your definitions. Okay, oh yes, here, we do have this. The measure of arc ZXY, that's a semicircle, that would be 180. We move on. All right, postulate 16 bothers me tremendously. There's nothing wrong with postulate 16 except for one little detail. It is very easily proved. What is a postulate? A postulate is supposed to be something that's so basic, so foundational, that we can't even prove it. It's at the very bottom of our geometry that everything else is built upon. Some of our postulates could be proved if this were a college-level geometry class. But folks, Postulate 16 is so easy to prove, I don't understand why these book writers called it a postulate. And I did look back at another geometry book I had that I used to use years ago, and in other geometry books, this is not a postulate, it's a theorem. This should be a theorem. In fact, we're going to take a couple minutes to prove it here in a moment. So, first of all, what does postulate 16 say? Postulate 16 says that if arc xz is 50 and arc xy is 80, guess what the measure of arc zy is? It'll be 50 plus 80. Kind of reminds you of, which is 130, kind of reminds you of angle addition. This is called arc addition. If two arcs are adjacent, meaning they share a common endpoint here, if two arcs are adjacent, then you can add the measures of the two little arcs to get the big arc. And if that doesn't make sense, then you need to get a cup of tea, because you're not awake. Okay, so 50 plus 80, the whole thing must be 130. Pretty simple. The book writers say that's a postulate. But folks, let's prove that. And at least in our minds, we're going to elevate it from being a postulate to being a theorem. Here's the proof. Here's our circle. We have arc xy. We have arc yz. Center is at O. All right, we're trying to prove that the measure of xy plus the measure of yz will equal the measure of xz. We are trying to prove postulate 16, which is not something that we normally would be trying to do. All right, we have our statements and our reasons. We'll start by saying, hey, statement number 1. The measure of arc xy, the measure of arc xy, is equal to the measure of angle xoy. Why would this arc measure be equal to this angle measure? Because that's the definition of arc measure. That's how we measure arcs. An arc's measure is equal to the measure of its central angle. So, of course, arc xy and angle xoy have the same measure. Well, likewise, true for arc yz. It's equal in measure to angle yoz, which we have here. And because these are two related statements and they have the same reason, we can just combine them into a single statement, statement 1. That way I don't have to write the reason multiple times. And by the way, how about arc xz? Isn't arc xz equal to the measure of arc xoz by definition? Yes, we'll throw that in there along with statement 1. So all three of these have the same reason, definition of arc measure. They're all pretty obvious. We lump them into one single statement. I'm not even sure I can remember a time when we've had 3 separate statements like that in one statement in a proof. Now, statement 2. I think we would all be agreed, if you remember chapter 1, you'll probably remember that the measure of xoy plus the measure of yoz must be equal to the measure of angle xoz. This angle measure plus that angle measure has to equal the whole thing. The two small angles add up to the whole thing. That was our old friend from way back in chapter 1. That was postulate 4. We call it the angle addition postulate. You can add this angle's measure plus that angle's measure. If that's 40 and that's 45, then the big angle must be 85. Angle addition. It's pretty straightforward. Now, this proof is so simple. It's why this should not be a postulate. Because all we have to do now is a bit of substitution. Do I see any place on the board another name for the measure of angle xoy? Ah, yes, right there. Xoy, let's change colors. Xoy is also known as arc xy, measure of arc xy. So I'm going to take that, which is actually that, and stick it in right here in the place of xoy. That's substitution. If I know that the measure of angle xoy is also known as xy, let's change it. Well, likewise, I'll change YOZ into arc YZ and stick it right there. And likewise, I'll change XOZ into its other name, which is arc XZ, and stick it in right there. So if I make, oh, that made an ugly mess. But if I make these substitutions, sticking this guy in here, this guy in here, and this guy in here because they're equal, what do I end up with? I end up with the measure of arc XY plus the measure of arc YZ equals the measure of arc XZ. And what did I do? That was a bunch of substitutions, right? That's the substitution property. And, well, there we go. I just proved it. I just proved that the measure of arc XY plus the measure of arc YZ has to be equal to the measure of arc XZ. Simple. Or very simply put, of course these arcs have to add up to the whole arc because their central angles add up to the whole central angle. In one simple sentence, that's the proof. So, yeah, we should not call this a postulate at all. We should call it theorem. If the book writers had made it a theorem, they would call it theorem 9.3 because that would be next in line. But they call it a postulate, so we'll just play along with them, okay? We'll refer to it as a postulate also. All right. Now, some examples. I've got two arcs. One goes from here to here, the other from here to here. We got a 40-degree arc and a 90-degree arc. So what's the measure of arc XZ? Arc XZ would be 40 plus 90, or 130. Pretty easy, right? Right, good. Let's move on. Now, what was the point of this? What was I getting at? Oh, yes. We already referred to this, really. Here we have two 40-degree arcs. We would be agreed, I think, that because they're on the same circle, they are clearly the same size and shape. They are the same length. They are truly congruent. But wait just a moment. If this arc is 40, what's this arc? Well, by definition, the arc measure is the same as its central angle, so that angle must be 40. But if this angle is 40, then by definition, this arc is no longer a question mark. It's also 40. But does that yellow arc and this red one, do they look like they're the same size? No. They are the same measure. They are 40 out of 360 degrees. They are 40 out of 360 degrees. They are the same measure, but they're not congruent. So again, as we said before, for two arcs to be congruent, what's required? They must be the same measure, and they must either be on the same circle or on two circles that happen to be congruent. So this arc is congruent to this arc because they're the same measure and they're on the same circle. This arc is congruent to this arc because they're the same measure and they're on the same circle. But these arcs are not congruent because they're not on congruent circles. Theorem 9.3. In the same circle, or in congruent circles, two minor arcs are congruent. What's that IFF mean? Yes, you remember this from back in chapter, I don't recall what chapter it was. IFF is a symbol that we can use for if and only if. It makes us a biconditional. Two minor arcs are congruent if and only if their central angles are congruent. Or because it's a biconditional, we could say it the other way around. Two central angles are congruent if and only if their minor arcs are congruent. As long as you're on the same circle or on congruent circles. Oops, went too far. This is not your assignment. So those of you who like to scan through the video looking for the assignment, you stumble on this page and see that, you're probably going to think this is the assignment, but if you're actually watching the video, you know that this is not the assignment. But I want to go through page 341, numbers 1 through 7 quickly as examples. So, number one, on page 341, number one says, use the letters shown in the diagram to name two central angles. Okay, a central angle, that's easy. A central angle. We're not naming arcs, we're measuring central angles. A central angle has the center of the circle as its vertex. So one central angle could be angle DOC. Another one could be COB. Another one could be BOA. Are there any other central angles? Yes, there are. We could have angle DOB. That's a different one. Or AOC. Or we could have central angle DOA, the diameter. As we said earlier, that's allowable in the rules of our geometry. So we've got lots of central angles. What's a central angle? It has to have the center of the circle as its vertex. All right, part B says name a semicircle. Well, we already did, really. Well, not really. We didn't name any arcs. A semicircle, we have only one that we can name. We could call this red guy right here, we can call that semicircle either arc DCA, or we could call it arc DBA. Is there any difference? No, there is no difference. They both start and end at the same place. The middle letter simply tells us that we are on this side of the circle. So there are two different, and I could reverse these. That's fine too. Why can't I name the white side over here? Well, because I don't have a point over there to name it with. If we had a point over here, we could name that semicircle as well. Part C, name two minor arcs. There are a total of 5 minor arcs we could name. DC, with the arc symbol, is a minor arc. Arc CB, arc BA. We could name arc DB. It's less than half a circle. Or we could name arc CA. Or we could name arc DA. No, we couldn't. Why not? Because DA is not less than half the circle. It's a semicircle. It's not a minor arc. The next question says, name two major arcs. Okay, we can handle that. More than half a circle. I'll just name one just to save some time here. One major arc would be, how about this green one? What green one? This green one. There's a major arc, more than half the circle. What's its name? Its name would be either arc CDA, or I could call it ADC. In this diagram, there is no other name I can give that arc, because between A and C, I only have one reference point. I've got to go through D. So we put D in the middle. These two arcs are the same arc. Okay, and then that was number, okay, how about number 2? Number 2 says find the measure of arc AB. The measure of arc AB, yeah, they gave it to us. Arc AB, we say the measure of arc AB, please get the symbolism correct, equals 50. Easy enough. Number 3 says, how about the measure of arc AC? The measure of arc AC, you have to employ, let's erase all this junk, you have to employ the arc addition postulate that we just proved a few moments ago. Arc, now I've forgotten what the arc was, it's AC. Arc AC from here to here would be a measure of 50 plus 80, otherwise known as 130. Okay, how about number 4, arc A major, well, maybe it's a major arc, no, arc ABD. What is arc ABD? Arc ABD, arc A, B, D is a semicircle. Therefore, its measure by definition is 180. Semicircles all have a measure of 180. How about number 5, arc BAD? That's a bad arc. Arc BAD. The measure of arc BAD would be the arc that starts at B, goes through A, and ends at D. That's arc BAD. So what is it? It's going to be 150, not 150. It's going to be 180 plus another 50. It'll be 230. By the way, if we take that 230 and add another 80 plus 50, if we add another 130, what should we get? Yeah, we get 360, the whole circle. What was it? That was, okay, how about arc CDA? Arc CDA, arc CDA. Oh, that one's also going to be the same thing. It's going to be 180 plus 50. It'll also be 230. And how about arc CDB? Arc CDB. Arc CDB. Arc CDB. The easiest way to do this one is we could say 180 plus 50 plus 50. Well, that's not hard because 50 plus 50 is 100, and another 180 is going to be 280. Or another way to do it is to say, isn't it going to be the whole circle minus 180, otherwise known as 360, minus 80, which would be, again, 280. Yeah, either way, it's your choice. It all makes sense. And then, let's take a look at number 8. Number 8 is asking for, and again, for those who are trying to scan through finding the assignment, this is not it. And if you're actually watching the video, you will know that this is not the assignment. Measure of angle GQF. Angle GQF, well, by definition, an arc's measure is equal to its central angle measure. Therefore, this also must be 60. Angle EQF. Angle EQF. Well, again, by definition, an arc's measure equals its central angle measure. So if that's 50, this is 50. Oh, these are so easy, aren't they? Measure of angle GQE. 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 Well, we could do it a couple ways. By angle addition, 60 plus, arc addition, 60 plus 50 is 110. Therefore, angle GQE must be 110. Or you could say to yourself, hey, if this is 60, then that's 60. And so the angle has to be 50 plus 60, or 110. Any way you look at it, it is 110. Then how about the measure of arc GE? The measure of arc GE, okay, arc addition, 60 plus 50, 110. Arc GHE, arc G, I don't see H. I left H off of the diagram. Where is H supposed to be? Oh, H is way over here. Forgot about him. Okay, arc GHE, arc GHE. Again, two ways to do it. No, actually there's only one way this time. So we just take 360, the whole circle, and subtract out 110. 360 minus 110 is 250. So it's got to be 250. And the last example, EHF. EHF. Where's EHF? EHF will be 360 minus 50, better known as 310. All right, so those are a bunch of good examples. What you might want to do is think through those again yourself, make sure you can do them all, then watch this part of the video again to make sure that you got them right. I would highly recommend that. Let's see, there's a warning regarding the actual assignment. On page 342, number 10, I've always considered the diagram to be a bit unclear. You can't tell for sure what the 2 refers to in that diagram for number 10. And this is really important. There are a number of questions in part 10, and if you don't get this right, then you do everything wrong. So I'm going to hold you to this. You're responsible to know this fact. That 2 in the diagram refers to angle CAO, not COA. I would suggest you take a look at the diagram in the book right now. Page 342. Look at the diagram for number 10. Look at that red angle number 2. And you'll see what I mean. It's a little bit unclear. I think it's kind of clear, but students often think it's not clear. That 2 refers to angle CAO, not COA. And on that note, here's your assignment. Page 341. Written exercises, meaning the bottom of the page, numbers 2 through 10 even. Page 341. Written exercises, numbers 2 through 10 even. And I've been getting a number of folks who have been asking me this strange question. When are these assignments due? Folks, an assignment given on Monday is going to be due on Wednesday. An assignment given on Wednesday is due on Friday. An assignment given on Friday is due on Monday. And all assignments are due at noon. It's as simple as that. Okay, so that's it for now. And stay tuned for the video giving you the answers and a discussion of this assignment. See you later.